Hey class, we're going to look at sequences in this video series. There's like 9 or 10 slides. The good news is each problem is very quick. So you'll notice in your homework there's quite a few assignments and there's 2 parts to the sequence homework links. I'm going to try to kind of cover both of those homework links in this video. So you'll start out with some problems where you're asked to write 3 or 4, or sometimes 5 terms of a sequence, and you'll be given the nth term, such as this one, where you have a sub n is equal to negative 2/3 all to the n power. The n is going to be your counting numbers, so you'll start with 1, substitute a 1 in for n, then you move up to 2, and so forth. So our very first term is called a sub 1. Whoops. And intuitively, just plug a 1 into the n, so that's negative 2/3 to the 1 power. What's that equal to? Negative 2/3. Then we move on to a sub 2. That'll be the next term in the series, or excuse me, sequence. We'll do series later. All right, so we're going to put in negative 2/3 quantity squared this time. And so if you take negative 2/3 times itself, you get a positive 4/9. And then finally a sub 3, negative 2/3 cubed. And let's take a moment. That's going to be negative 2 cubed, which is negative 8. 3 cubed, which is 27. And so your third term is going to be negative 8/27. Okay, so that's precisely how you would approach the first problems in your homework link. Let's move on to the next slide. This one's called a recursive formula, and we have a first term given, and then the next one is the formula that allows you to cycle in your previous answer. For example, a sub 2, which would mean k has to be 1 in order to make that a total of 2 under there. That's basically 2 times your first term plus 1. So that's 2 times 3 plus 1. What does that give us? 7. Now that answer gets cycled back into the k equation. A3, that's 2 times a sub 2 plus 1. So you're constantly recycling the previous answer into the k formula right there. Okay, so our previous answer was 7, so that's 2 times 7 plus 1. And what's that total? 15. All right, so that's the first 3 terms of that recursive sequence. Next slide, we're going to look at simplifying a factorial ratio. Factorial is consecutive multiplication. And I wrote in the note here that n factorial is defined as n times n minus 1. If we were to do this with numbers, like, for example, 4 factorial, you start at the number, sequentially count down, and multiply as you go. So the 4 factorial would be 4 times 3 times 2 times 1. How much is that? That's right, 24. Okay, so let's take our factorial ratio and a good strategy is to take the larger one, like in this case our denominator, And we can start with the original term, count down, and if we can get it to look like our numerator, you can actually stop with the next term and give it the factorial. Okay, so if you think about the numerator, that's 3n plus 1 times 3 to the n. Everything from this term downward, let's make sure you can see that. If I take off that factorial in the numerator, and I count it down 1, see how we get that cancellation? The upper terms remain, and since our numerator canceled all the way out, there's an understood 1. So this would be our simplified ratio right there. Of course, if you have questions, send me an email. I'll be happy to go over. Our next slide, we're going to start looking at finding the limit of the nth term of a sequence. Basically, from Cal 1, you remember taking, finding limit values as n approached infinity. Same thing here. Whoops, let me switch that back to black ink. Here we go. Okay, so each one of these, we're going to take the limit as n approaches infinity of our nth term. For this particular problem, as n gets really large, the 7 will fade away. It won't matter that much once you get n really dialed up large. So this will be equal to the limit as n goes to infinity of 5n over 5n. And what do we get when we take a number divided by itself? You got it, 1. When n approaches infinity on this next nth term of a sequence, the numerator is fixed this time. When you hold a numerator fixed, but you allow your denominator to run amok and it becomes very large, you can think of it as taking a cake. The more slices you make into that cake, the smaller each piece gets. So this one's got a limit of 0. Sometimes the limits aren't just as clear as they were on the previous slide. Let's also remember a skill from Cal 1 called L'Hopital's rule. If we let n go to infinity for this term, natural log of n squared over 3n, 3 times something super large is super large. It goes to infinity. Natural log of something large also does. So this is a case of infinity over infinity. I'm going to make a little note of that. It's an indeterminate form, which is okay. By L'Hopital's rule, we can take the limit, or excuse me, I was trying to write and talk. We can take the derivative of the numerator and derivative of the denominator separately. The numerator, natural log of n squared, its derivative is 2n over n squared. derivative over original. And you've heard me say that from previous videos. The denominator's derivative is 3. So this simplifies to 2n over 3n squared. Cleaning it up a little bit, in fact, let's cancel an n from top and bottom. And just like the previous slide, we now have a ratio with a fixed numerator and a denominator that goes out of control. So as n gets really large, the fraction gets really small. You guessed it, 0. Very good. Back to a factorial. We're going to let the limit as n goes to infinity. I'm going to rewrite the denominator so that it will match the numerator. The denominator starts with a larger term, n, instead of n minus 2. So what I'm going to do is I'm going to rewrite that as n times n minus 1 times n minus 2. Now, if we kept counting it down, n minus 3 all the way to 1, that's fine. But wherever you stop in the downward consecutive counting, like if I want to stop at this term, I put the factorial back on it. The idea is to get a match top and bottom so you can cancel. Rewrite your term. The entire numerator got canceled, so that's a 1. The denominator is n times n minus 1. And if you let n get super large, what happens to the value overall? That's right, approaches 0. Very good. Okay, so we're really good at fixed numerators and growing denominators. That goes to 0. That's going to help us on finding the limit of this nth term of a sequence. As we allow n to get super large, what does this approach as n gets really large? That's right, 0. And what is 3 to the 0 power? That's right, 1. Very good. So these problems are pretty quick. It's just a matter of being exposed to the different types that you have. Let's move on to the next slide. This is one of my favorites. Let's recall the graph of sine. Sine oscillates back and forth. Let me see if I can't do a little better job of drawing that one. Okay, so it oscillates up and down and back, over and over. Does anybody remember the top and bottom values there? They were the amplitude of 1 values for sine. That's right, positive and negative 1. That's going to help us here. If we look at the original nth term, sine is always going to be equal to or less than 1. And if you look back at that graph at the bottom of your screen, that's the max sign of a variable. As the n gets larger and larger, it just oscillates back and forth. It never goes above 1. On the bottom of the graph, the low end, what's the smallest that sine ever gets? That's right, -1. Both of the end limits, you have a fixed numerator and an increasing denominator. What does that do for the overall limit? You got it. Those are 0. This is called squeeze theorem. The numerator fluctuates between -1 and +1 throughout its entire life cycle. The denominator grows larger and larger and larger. So by squeezing that in, what do you think the limit of this term is? That's right, it's also 0. Very good. In the second part of your homework, you're going to be asked to come up with an nth term for a sequence of terms that are going to be given. Basically, it's trying to find a pattern, and you'll always be asked to do it for n equals starting at 1 and getting larger. It's just basically the natural set of numbers. Okay, so if we think of 10 as 9 plus 1, our next term is 9 plus a half, 9 plus 1/3, excuse me. And so on. I feel comfortable writing the nth term as 9 plus 1 over n. And if n starts at 1 and consecutively counts upward, I believe we've got our term. Do you guys agree? Okay, perfect. The next sequence, 1 over 4 times 5, 2 over 5 times 6, there's definitely a pattern there. We just need to make sure it fits where when we write the nth term that it applies for 1, then 2, and 3, and so forth. Well, since the numerator begins with 1, I feel pretty good about writing n as the numerator, because that will be 1, 2, 3, 4 across the top. In the bottom 4, that's 1 plus 3. And that will seem to be the first number of the denominator. When n is 1, it starts with 4. When n is 2, it makes it 5. When n is 3, it makes it 6, and so forth. The second number on the denominator is 1 plus 4. The next fraction, it's 2 plus 4, and so on. So I feel pretty good about writing that as my nth term of the sequence. And finally we have the nth term of a sequence given, but we're going to go through some vocab, monotonic and bounded. Monotonic is just to make sure that as n gets larger, starting with 1, then 2, like if you were to write out a bunch of the terms like we did in the very first slide, to see if those values head in one direction, like do they keep getting larger or do they keep getting smaller. The bounded part is if we determine the terms get larger and larger, is there a finite value that they approach and never go past? It's like if the sequence climbs, is there a roof? If the sequence decreases, is there a basement? So we're going to look for increasing or decreasing all the time, that's monotonic, and bounded if there's a limit that will stop the increase or decrease. Okay. Basically, you want to know if this thing increases or decreases. So it's going to be one of these two cases if the sequence is monotonic. Either the next term is going to be larger than the one before it, or it will be smaller than the one before it. So I'm going to take 3n over n plus 2. I'm not going to put an inequality symbol on it yet because I don't know which way it's going to go. You could write out a list of A1, A2, A3, and that may actually be a better approach. The inequality statements, like one of those two, either the left or the right, is kind of a more official way to look at it. I'm going to replace the n's with n plus 1. All right, I'm going to switch to the next slide. Actually, let me clean it up here, and then we'll switch to a clean slide. So that tells us that no matter what, our next term is going to be greater than the one before it. So that's increasing, monotonic. The terms will always increase. Of our original nth term, 3n, picking up where I left, whoops, not sure what happened there. Picking up where I left off. And making sure that I didn't have a copy error. Let's cross multiply. Foil. Okay, so I'm going to go ahead and make the claim that the right side is larger than the left side. In your mind, let's let n be 1. Substitute 1 in for the n's, and you get 3 times 1 plus 6 times 1 plus 6, which is, what, 15? That's greater than 9. If you let n be 2, then you get 3 times 4 plus 6 times 2. So that's 12, another 12 and 6, that's 30. But you can tell now that from n equals 1 all the way up to however far you want to count, the right side is always going to be greater than the left side. I'm going to go back to the previous slide. Now, if we go back and take the limit over n plus 2, once n gets really large, the plus 2 on bottom doesn't amount to much, so you get 3n over n. Canceling the n's gives you 3. So that turns out that this sequence is monotonic because each term keeps getting larger and larger, but it is bounded above by 3. Bounded above. And monotonic. Okay, so let's go back. Remember on that next to last slide how I said it's really not the official way to do it, but you can absolutely use intuition on here. Math is pretty intuitive. If you look at each term, I'm just going to look at the first 3. If you let n be 1, you have 3 over, well, I'll just do it officially, 3 times 1 over 1 plus 2. 3 over 3, which is 1. The second term, 3 times 2 over 2 plus 2. That's 6 over 4, which is 1.5. The third term is 3 times 3 over 3 plus 2. 9 over 5. Which is 1.8. And if you see how these terms get larger as you go, they keep getting larger. That's monotonic. And if you were to keep building like all the way up to like a sub 200, you would be approaching 3. I hope this video helps.